This lecture, we're going to do an example of determining what our shear stress distribution or our shear flow is in a thin-walled eye section, and we're going to do it with no numbers. We're just going to do it with variables, really just to try to sort of hopefully towards the end of it we can find some rules with respect to if we've got flanges or if we have a web as to how our shear flow or our shear stress is going to vary along the portion of the section, so be it a flange or be it a web. So you can see the example that we have here. So we just have an eye section with depth D, width B, and the flanges and the web all have the same thickness T. And it's given us the neutral axis, or the centroid location is at D over 2, so it's a symmetric section, so of course that's going to be where it's going to be located. And what we need to do is plot the shear flow in the section. So just like when we approach the shear stress problems, first thing we want to do is look at, well, what clues do we have and what do we need? Well, if we need to plot the shear flow, we should probably use the equation for shear flow, which is, as you recall, little q equals VQ over I. So for a given section, our shear force applied to the section V is going to be constant, and our moment of inertia, I, is going to be constant. So really, the only thing that we need to find is this Q as we move around the section. So now, well, where do we start? Well, we looked in our introduction lecture to shear flow. We were looking in the flanges. So, always a good method is, when in doubt, draw a free body diagram. So if we want to determine what our shear flow is as we move along the flange, well, let's just draw a free body diagram of the flange. So, and we'll just give that, we'll just call that point A. So our free body diagram at A, and remember this is just our flange here. In fact, even to make this even a bit more clear, let's just draw what portion this is coming out of the section. So if we just sort of dash the section in here, so if that's the outline of the section, there's some distance, D over 2. And really, this free body diagram here is going to be located, right in this. It's really this little block that we're looking at in from the flange. And if we draw the stresses on it, well, we know that, well, if let's assume that the top is in compression. It's a beam under positive bending. So we're going to have shear stress. So we're going to have our normal stress, pressing in. So we're going to be in compression. From our normal stress. And just like in the introduction to our shear stress, or to our shear flow in thin wall sections, remember that in order to have shear, we need to have a difference in moment across the section. So we're going to have also a difference in bending stress. So this little delta sigma. And in order for these forces to be balanced out, well, there has to be a shear force or shear stress tau going this way. And then in order for this little block to be in equilibrium, well, this longitudinal shear force is going to have to get balanced by one going in this direction. And again, we've got tau equals 0 on the top and the bottom. So that's what our forces look like. Now, let's just put some numbers to this. So say, numbers. Let's put some values to this. So let's say that this little block is really some distance x from the center of the member. And so and that just sort of puts it in space. So this distance here to here is going to really be just b over 2 minus x. So, let's just look at our shear flow equations then. So, again, we've got shear flow to the right. That's just what we see here. And so if we look at our shear flow equations, Q equals V Q over I. As we said previously, V and I are constants. And if we remember big Q just equals A1, Y1. So it's the same A1, Y1. It's defined the same way as we did when we looked at finding shear stress tau equals VQ over IT. So A1 is really just going to be the area that we're looking at, which is on one side of the cut, and then it's its distance away from the neutral axis, which is going to be our centroid. So our A1 here is going to be this little area right there. So we'll label that A1, and just for reference, the web thickness here is going to be some value T, and the Y1 is just going to be the distance from the centroid of A1 to the neutral axis. So the centroid of A1 is just right in the middle here, so at sort of T divided by 2 of that little block. And then our distance to the neutral axis is Y1. So even though we're looking at it slightly differently than how we've done these previous I sections, when we assumed just the shear went straight down instead of towards the center and flowing around, our Q is defined really the same way. It's just going to be the area sort of away from the cut, so to speak, and then Y1 is just going to be the distance of that area to the centroid. So now, let's try to put this together in terms of what our A1 and Y1 are going to be. So A1 is really going to be the thickness. So A1 equals the thickness T times this distance. And so this distance is just going to be B over 2 minus X. And so Y1, now Y1, so say, A1 you can see how A1 will get bigger as we move closer and closer to the center, till eventually, when x equals 0, A1 is just going to be the thickness T times B over 2. But how does Y1 change? Well, Y1 really doesn't change. So if A1 is really small, the distance between the centroid of A1 and the neutral axis, so down here, neutral axis, of the section doesn't change. It doesn't matter how much bigger this gets. The centroid of A1 is always going to be located, a height T over 2. It's going to be right in the middle here. And that distance to the neutral axis doesn't change. So Y1 equals just D over 2, so half the height, minus, the half the height of the thickness here, minus T over 2. And so that's going to be the same all the way across. So if we put all of this together, we get, Q of the flange equals our shear force V times T times B divided by 2 minus X. And again, all of that is A1 times D over 2 minus T over 2. And that's Y1. And all of that is divided by the moment of inertia. So that's the expression for the shear flow in the flange. And what's interesting here is that as we move along the flange, our shear flow, so the only variable which changes is this variable x. Everything else here is a constant. V is a constant, I is a constant, moment of inertia is constant. The thickness, the width, the depth of the section, all constant. The only thing which is changing is where we're taking this cut relative to the center line. And what you'll see is it only varies by a factor of x. And so it's going to vary linearly. So what we find is that, the shear flow in the flange varies linearly as it moves towards the web. So that's an important bit. And again, just sort of knowing what we know about our rules, we know at the edge we've got no shear stress. So our shear flow, or so how it changes with time, it's not with time, with distance from the edge, is at edge it equals 0, and then at web equals its maximum. So our shear flow, if we're to plot it as we move across, it's going to look something like that. With, again, if we look at our little free body diagram, we know our shear is pointing towards the web. So that's the first flange. But if we want to find out, what is our equation for our shear flow in the others? Well, what we can do is again sort of draw a free body diagram of all of them. So let me zoom out just a bit for you there so you can kind of see everything. And this is what we've done. So we just did this one up on the top right. And, you can see that, we've got our unbalanced force here. So we got to push a little bit further. And that's just what we showed over here. On the other side, so let's go through and just sort of draw out what the sort of directions of our shear flow are going to be for each of these. So on the top left, we just worked that out. We know our shear flow is going to go towards the middle there. And so if we go to the other side of the compression flange, again, we see we've got sigma and sigma plus delta sigma. In order to balance this out, we need a little shear stress going in this direction. And so because we need to have our corners in equilibrium, just sort of remember our arrows for shear always point towards arrows. Tails always point towards tails. So this means that our shear stress, or shear flow in the other flange is also going to go towards the web. Well, now let's look at the tension side. So we've got our stresses pulling away. Again, d sigma is going to be sort of on the face closest to us. So in order to balance it, so we've got a bigger tension force here, well, we need to give it a little bump going this direction. So it goes that way. And again, so if tails have to touch tails at a corner and tips of arrows have to touch tips, that means our shear is going to go in this direction. So our shear is looking like that. And our final side, again, you can kind of see the pattern. We've got more stress over here, so we've got a balance. So we've got more stress pulling it down this way. That shear stress has to help balance it. It's going to go this direction, and so that means our shear flow points out that way. Now, so we now know the directions for all of them, and it's kind of, in compression, they're going towards the web, and then in tension they're going away. And now the question comes, well, what is the value? Well, if we set all of our equations up with, we call this some distance x from the middle, and this is going to be b over 2, and we have our depth, d over 2, and our thickness is t for both of those. Well, really, this is the exact same equation which we just worked out over here. It's the same variables. So our shear and our flanges are all going to be equal, the sort of equal in magnitude with respect to distance away from the web, or conversely, distance away from the edge. So Q flange for all flanges is going to equal V times T times B divided by 2 minus X times D over 2 minus T over 2 divided by I. So that's going to be for all of the flanges. And because we have to have zero shear at a free edge, if we sort of draw what our flanges look like in terms of what the shear flow distribution is, well, we know that if we're starting, we've got to start at 0 for all of them. And well, we're going to rise to a maximum and we're going this direction here, and we're going to start from maximum and go this direction here. Well, we know we're 0. Well, our shear flow is essentially just going to go, it's going to be negative down here, and going to be similar down here. So that's what our shear flow distribution looks like in the flanges, and it's really the the magnitudes make sense here, and then it's really just a fact of looking at what our forces are going to be, and then the signs really are just dependent upon which way your tension or your compression forces are going. So that's the flanges. Now let's have a look at what our shear flow and shear stress distribution is going to be like in the web. So we see the flanges is going to be linear. Let's have a look at the web. So we have shear flow in the web. Just like before, let's work out. Let's just draw ourselves our diagram, and a little picture can kind of help us figure out what our various values are. And we'll just go ahead and dash in the rest just to make it clear what portions are participating. So we'll put ourselves some dimensions here, d over 2, d over 2. It has a width b, and say we want to take in this portion of the web. So if our shear flow equation is going to be Q equals V Q over I, well, again, just like for the flanges, V and I are constants. In Q, we can do the exact same thing we did when we were working out shear stress tau in the web of an I section, and we can think of it as really a it's the participation of this chunk trying to resist shear. So it's what the applied bending stress is over this area is the shear force here, which is going to kind of help balance it. But we can either figure out. So remember, it's going to be A1 times Y1. Well, or as sort of a shortcut, if we've got these compound sections, is we can think of it as really the sum of these two areas. So sum of A1I, Y1I. So just the exact same way that we worked out the shear stress in the web of an I section using tau equals VQ over IT. And so if we do that, our distance y is here. We have y1 web, and that's a1 web. This is a1 flange. And this is our distance, y1 of the flange. All right, with all of that, well, we can work out what Q is, and if we can work out Q with our sort of respect to our distance y from our neutral axis, then we know what our shear flow is and how our shear flow is distributed down the height. So, for our flange, A1 flange just equals the thickness, T, times the width, B. And then y1 of the flange is going to be the distance between the centroid of A1 flange to the neutral axis of our section. And so that's just going to be d over 2 minus the thickness over 2, because the centroid's right there in the middle for a rectangle. So that is d over 2 minus t over 2. All right, so that's our first bit that we're going to add in. Now for the web. A1 of the web equals, well, it's the thickness of the web. So again, that's just a value of t times this distance here. So the top of this is just going to be d over 2 minus the thickness, and then the bottom is y. So you can kind of think of it as d over 2 minus the thickness minus y gives us this distance for the other part of our area. So it's just going to be d over 2 minus t minus y. And y1 of the web is just going to be, well, it's halfway between y and d over 2 minus t. So it's just because it's halfway, that's the same as the average there. So let's just put that in. So that's going to be 1 over 2 times y plus d over 2 minus t. All right, so to put all of this together, we just sort of sum up our each A1 times Y1, and that gets us our Q for all of this section here. So we have Q equals the first bit, which is just the thickness T times the width of the flange, and that's our A1 times d over 2 minus t over 2. So that's going to be the contribution from the flange. And then we sum up and add in the component from the web. That's t times d over 2 minus t minus y multiplied by one over 2 times y plus d over 2 minus t. And if we rearrange this a bit, we get Q equals T times B times D over 2 minus T over 2 plus T over 2 times d over 2 minus t squared minus y squared. And you can see it's this y squared here is, everything else here is a constant. So the only variable which is changing is our distance y, and so that means Q is going to vary parabolically. And so if we put our big Q into our shear flow equation, we get V times T times B times D over 2 minus T over 2 plus, put those in brackets, t over 2 times d over 2 minus t squared minus y squared all over I. You can see that our shear flow, the only variable which is changing is this distance y from the neutral axis, and that means that our shear flow is going to be proportional to a change which is parabolic, which is just the same as with our shear stress. So that's kind of neat. That means that when we looked at our shear stress, we kind of had the right model there for members which are parallel to the axis of loading. So it's worth writing down. So the shear flow in the web varies parabolically with depth. And so, well, that's cool. So now we can go ahead and plot up what our sort of shear flow is going to look like over the section. So we've got the flanges done, and now we've got the web done. Well, let's plot that up. So we know that we've got to be 0 at each free edge. We saw with our flanges that we start at 0 and we move up to sort of a maximum value at the web, and our shear flow is going to go towards the web on the compression side, and then away from the web at the tension side. We'll work this out when we do an example with some numbers, but this value here of Q and this value here of Q is going to be equal to the value in our web Q and Q. And that's just because we need everything to be in equilibrium. And the shear flow is going to go pointing down for our web. So that's kind of what our shear flow distribution looks like over an I section. Now, if we went through and we integrated sort of the areas here, and we So if we integrated the shear flows, we would end up with forces. And those forces would look like this, where you'd have a force in the flange, so FF, and it's going FF, and then we would have a force in the web. So I bring that up just because this will become really important when we look at asymmetrical sections, so particularly channels. But that's coming attractions. But before we wrap this up, some important things to note. So we did this for an I section, but you can see where, if you were working out the shear flow for any member which was horizontal, well, Y1 never changes. The only thing that changes is our A1, and that's going to change linearly based upon where we're located in the section. Similarly, for a vertical section, and this is all assuming that we've got a force pointing down. So you might think about it as a portion of the section which is perpendicular to the load, so hence it shows up as horizontal here, or one which is parallel to the load, so vertical here. So the vertical one, because our y1 is going to be changing in our constantly, that means that it's going to be changing with respect to y. We're going to move parabolically. So for shear, so when we're looking at shear flow in thin wall sections, we can come up with kind of these two rules. So and I'll write them out explicitly. So sections, and we'll say these have to be loaded in a principal axis. We'll talk about this in a moment. But for thin wall sections loaded in a principal axis, shear flow varies linearly in horizontal pieces. And shear flow varies parabolically in vertical pieces. And so those are really powerful things to note, because it's kind of true for any section like this. So whether we're looking at a box section or a C-section. Now the big thing is it has to be loaded in the direction of principal axes. So because we've got symmetry here, if our load is coming straight down, well, then our principal axes will be sort of our Cartesian, sort of our x and our y. If we had a biaxial load, as you've worked out before, your principal axis shifts, and so this no longer works. This is why you're not going to be able to do this with like a Z section, so something that looked like this, because the principal axes are here. So that doesn't work. But for a an I section, a box section, a channel section, they all work really, really well. So we'll just leave you with this this bit here. So this is just keep in mind that when you're looking at shear flow in thin wall sections, if you're loading the principal axes, you're going to vary linearly on a horizontal portion, and you're going to vary parabolically on a vertical piece, and your shear flows have to be in equilibrium where those meet. So that wraps up this lecture. The next one we're going to look at is we're going to do this, but we're going to do it with some numbers, and hopefully that will help solidify this. So with that, thank you very much.